Okay, so this chapter is about fixed axis rotation. Okay, so what we'll do is we'll study a rigid object. So this is a rigid object that is rotating about that axis. Okay. Now, so in the first 9 chapters, you studied a object in doing translational motion. Okay. Here, every point in the object had the same velocity and so on. So you were able to treat this object as a point object. Okay. And you studied the motion of this object. So for instance, you were interested in knowing where the location, where the object is at all times, and you could calculate the velocity and acceleration for that guy. And if the acceleration was constant, you were able to say things like the following: at and so on. X minus x naught was equal to v naught t plus 1/2 at squared. Okay. So you were able to say things like that about this motion. All right. Now here's the problem with this guy. Okay. So when this guy rotates, you see this point is going at a bigger circle than this guy. Somebody halfway is making a smaller circle, but they are going around in the same time. So the velocities are different. Different points are moving at different velocities. So it seems like this is a much more complicated problem. Okay, so when this guy moved, the displacement of every point, the distance that every point moved was the same. Is there anything that is the same about this motion?
If you look at a point that's like each blade, if you look at the same exact length on each blade, and those be the same speed, that's what you're asking.
So it turns out that, let's say this is the x-axis, and you measure the angle through which each point rotates. That is the same. Okay, so we'll use that as the coordinate to describe the motion of this object. Okay, so once you realize that, so let's say this is the x-axis, we'll measure the angular position of the object with reference to x-axis. Okay, so if you describe the configuration of the object as the angular position, okay, with reference to some axis, every point is rotating through the same angle. Okay, and now you see this is the angular position as a function of time describes the motion of this guy, and everything that you've derived over here can be translated to this object. Okay, so it'll be very similar to that. So the formula that we've derived in the first 9 chapters for translational motion, we'll do that for rotational motion in 1 chapter. Actually, we'll do it in 2 chapters, chapter 10 and 11. Okay. Now, for this to be true, this has to be a rigid object. So for instance, if you had a cup of coffee and you were stirring the coffee near the walls doesn't rotate as much as this coffee does. Okay, so it won't work for fluids. Okay. So we'll talk about rigid objects. Okay. Now I'm recording this, but I can show you this to you guys here with this bicycle wheel. So in the first 9 chapters, what we did was we studied translational motion. Every point on the wheel moved at the same velocity, same displacement and all. So you could treat this as a point object. Okay. Well, that's a bad use of a wheel. What you really want to do is this. Okay. So you see that's a fixed axis, this is a rigid object. Every point on this wheel rotates through the same angle. Okay. So that's the coordinate we'll use to describe the motion. Okay. So, so here's a object, rigid object. We'll measure its configuration with reference to this line, and when this rotates, okay, there is the angular position of the object. Just like this is just like when you had an x-axis. This was the origin, and the position of this object was given with reference to the origin. Just like that, we're giving the angular position with reference to this reference line. Okay. Now we'll do the following. So we'll agree to the following. So this is 45 degrees. We'll do the angles in radians. If it rotated through here, how much did it rotate through? So there's the object. I take this point, and what angle did the object rotate through? 360. Yeah, 720, so we keep adding the angles, okay? All right, so let's say I'll do a motion. I went like that, oops. Okay, so I grab hold of this thing, go like this, then go back. So that's a motion. Okay. How many different kinds of motions can I do? Infinitely many. Okay, so if I want to describe a motion, what is the best way to describe that motion? What was the best way for you to describe the motion of this object? Yep, x as a function of time. So similarly, if you want to describe the rotational motion, this is the most useful way of describing the motion. Okay, what we want to know is the angular position of this object as a function of time. Okay. All right, so okay. So if you had the position of that object as a function of time, I'm going to just make up a function, let's say 5t cubed plus 6t squared plus 7t plus 10. Once you had the position as a function of time, what could you do? You could calculate the velocity of the object, which was dx by dt. 15t squared plus 12t plus 7. Okay. You could calculate the acceleration of the object. And so on. That's what you were interested in. So just like that, if you're given the angular position of that object as a function of time, yeah, we will define angular velocity denoted by omega, which will be d theta by dt. Okay. So anybody want to help me out? We'll define something called angular acceleration. Okay. Okay. So if this was measured in meters, this would be meters per second, assuming time is in seconds, and this would be meters per second squared. If this angle was measured in radians, this would be radians per second. This would be radians per second squared. Okay. So we will look at the motion of a rigid object. Okay. So let's go back to. So we'll look at the motion of a rigid object about a fixed axis. Okay. Right now the axis is at rest. For these guys, actually, the axis won't be at rest. The windmills face the wind, they change directions, but we'll assume that the axis is rigid. Okay. So that's what the title of this chapter is: fixed axis rotation of a rigid object. Okay. And how do you describe the motion? You just give the configuration of the object as a function of time. And that was the parameter, or that was the coordinate used to measure the configuration of the object. Okay. All right, so rotational variables, angular position, we've already told you that. We'll talk about angular velocity and angular acceleration. I've given you an example. Okay. And then we'll study all of this. You'll see moment of inertia. Okay. So over the next 2 chapters, you will learn, if you do the following replacement, you replace x by theta, velocity by angular velocity, linear acceleration by angular acceleration, mass by something called moment of inertia, okay, force by something called torque, okay, linear momentum by something called angular momentum, I times omega, and so on, okay. So if you do this replacement for these guys, if you replace by these quantities, you'll get the corresponding equations, okay. So every equation that you learned in the first 9 chapters, you do this replacement and you get the corresponding equations for rotational motion, okay. So for instance, when A is constant, x minus x naught was equal to v naught t plus 1/2 at squared. So what would be the corresponding equation for rotational motion? Alpha is constant, that is angular acceleration is constant. Theta minus theta naught, that is the final angular position minus initial angular position, is equal to initial angular velocity plus 1/2 alpha times t squared. What is Newton's second law? Force equal to mass times acceleration. Torque will equal, mass gets replaced by moment of inertia times alpha. What is the grown-up version of Newton's second law? This was a special case. Here is the grown-up version, dp by dt. Okay. And so for Newton's second law for rotational motion will be dl by dt. Okay. Again, these are vector equations and so on. Okay. But so that's what we're going to learn in this chapter. Okay. So corresponding to every equation that you've learned for linear motion, you learn the corresponding equation for rotational motion. Okay. All right. So here's a centrifuge where you can subject astronauts up to 20 Gs. Okay. So let's say if the Earth's gravity suddenly increased to 20 Gs, what will happen? All my blood will collect in my feet. Okay, and I'll pass out in a couple of seconds, and you won't have to worry about this chapter anymore. You probably will. All right. When an extended object rotates, all parts of the object do not have the same linear velocity or acceleration. The motion of the object cannot be analyzed by treating it as a particle. Okay, so for rigid objects rotating about a fixed axis, all parts of the object rotate through the same angle, and that's the coordinate we'll use to give its configuration, okay, describe its configuration. So here's an object. We'll use a reference line to give the position of the object. We will mark a point on the object and see how much it's rotated through from the reference line. Okay. So here there's the starting position, there's the initial position, and the object rotated through this angle theta. Okay, so that's its configuration right now. All right, theta is related to the distance that this object moved, and r is the distance from the axis of rotation. So the axis of rotation is coming out of the plane of the paper. So theta is s divided by r. What are the units for s? Meters. What are the units for r? Okay, what are the units for theta? Nothing. Okay, so this is given an artificial label, radians. Okay, and so theta is a dimensionless quantity, and it's given the artificial unit radians. And 1 radian is roughly about 60 degrees. Okay, 57 and change. Okay, so when an object moved from here to there, the displacement was given by delta x was given by x final minus x initial. Okay, so this displacement delta x is x final minus x initial. So here is this object that rotated from this initial position to that final position. So the angular displacement is given by theta f minus theta initial. Now, so the formula is very similar. Okay, it turns out that okay, now this is just technical detail, and you would need to know if you're a physics major. This is a vector. Okay, it turns out that this guy is not a vector. It's a vector for only infinitesimal quantities. Okay. But we won't worry about that. Okay, so all right, angular speed. Angular speed is, the RPMs and all that you hear about. Okay, so if something is rotating at 1,000 RPM, what does that mean? 1,000 RPM? I'm sorry? Yeah, 1,000 revolutions per minute. Okay, so angular speed, it's denoted by omega. The average angular speed is the angle through which you rotated and the time over which you rotated. Okay, and see, this is just the parallel of average speed was displacement over time. Okay, so any formula that you see, there is a corresponding formula that you learned less than a month ago. Okay. Yes, so displacement over time. Okay, average angular velocity is displacement over time. We, of course, are interested in the instantaneous angular speed, that is in the limit delta t going to 0, which is d theta by dt. Okay, so we will be interested in somebody will describe you a motion, and you'll be interested in the instantaneous angular speed, or will tell you what is the direction in a second. So instantaneous angular velocity, which is d theta by dt. And if this guy is a function of time, then you are accelerating. Just like when velocity is changing with time, you're accelerating. So if your angular velocity is a function of time, then you have an acceleration. Okay, so this is the angular velocity. Here's the direction of the velocity. So for one-dimensional linear motion, which way could the velocity point? Either to the right or to the left. Okay, so for 1D motion. So this guy was, by convention, these guys, so you didn't need a number for the direction of the velocity. How did we indicate the direction of the velocity? By using a sign. So this was plus 7 meters per second. This was minus 5 meters per second. Okay, the sign told you the direction. Okay, just like that, for a rigid object rotating about a fixed axis, the velocity vector, angular velocity vector, either points in this direction, it points along the axis, either in that direction or this direction. Okay, so that's the direction of the velocity. And here's the rule: you use your right hand, and if your fingers point in the direction in which the object is rotating, the your thumb points in the direction of the velocity. Okay, you got to use your right hand. And if the convention is, if this is rotating counterclockwise, that velocity is positive. A clockwise rotation is a negative velocity. Okay. So of course you have to look at, so this depends on the perspective. If you're looking at from this side, this is counterclockwise, and if you're looking at from this side, this would be counterclockwise. Okay. So, all right. So you can't change your relative. Okay. So counterclockwise rotations are positive, clockwise rotations are negative. Okay. And the velocity vector is always pointing along the axis. When do you accelerate? When your velocity changes. Okay. So if angular velocity is changing, so there is a change in angular velocity, final velocity minus initial velocity, divided by the time over which that change happened, then you're accelerating. Okay. Instantaneous angular acceleration is d omega by dt. Okay. And so that's your angular acceleration. Okay. So so let's do the following. Okay, so if something is spinning this way, and if it speeds up, then, okay, so before I do that, let's do this. Okay, so here's, again, you want to look back at 1D motion. So everything we are doing here has a parallel in one-dimensional motion. Okay. All right, which way is acceleration? Is this object accelerating? Yes. And the acceleration vector is pointing in that direction. Okay. So you see, if the magnitude of the velocity increases, then the acceleration vector is pointing in the same direction. Okay. And if the magnitude of the velocity is decreasing, the acceleration vector is pointing in the same opposite direction. So just like that, if an object is spinning and it starts spinning faster, then the acceleration vector points in the same direction as the velocity vector. Okay? If the object is spinning and if it's slowing down, then the acceleration vector points in the opposite direction. Okay? So let me illustrate this using this bicycle wheel. All right. So here I'm spinning this wheel. Which way is the velocity right now? So here you point your fingers in the direction, and that's the direction of the velocity. Acceleration was pointing in the same direction. Okay. Now, if it's slowing down, the velocity is still in that direction, but the acceleration was in the opposite direction. Okay. All right, so you spin faster, the acceleration is pointing in the same direction. If you're slowing down, then the acceleration is in the opposite direction. Okay. So again, for finite displacements, okay, angular displacement, it's not a vector, but for infinitesimal displacement, angular displacement, it's a vector. Okay, again, you don't have to know this. So all this is doing is, so this diagram should be ds for small displacements, r d theta. Okay, so what this is showing you is the vector relationship, the cross product, d theta cross r is ds. Okay, the small displacement of this point. Okay, again, we won't worry about that. Okay, so ds is that. If you take the time derivative of this, d theta by dt, so this would be velocity. If you take the time derivative of that, dt, so this would be velocity of this point equal to omega cross r. And that's what this formula is. Okay, so when an object is spinning, the velocity of this point is given by omega. Omega is that vector over there, cross r. R is that vector. Yeah. the further out you are, the faster you're moving. The bigger this is, the faster you're moving. So this formula is relating the angular velocity of the object to the linear velocity of a point on the object. Okay. And again, if you take the time derivative, that will give you the acceleration. This time derivative, that will give you the angular acceleration. So this is tangential acceleration. Tangential acceleration is the acceleration that is arising because the speed change of the object. The tangential acceleration is angular acceleration cross r. Again, the further out you are, the faster you're accelerating. Yeah. All right, we can stop here.